All right, here we have our four carboxylic acid derivatives. We have an acid chloride, we have an anhydride, we have an ester, and we have an amide. They are arranged in order of leaving group ability, right? So ignore that. In order of leaving group ability. So the best leaving group is up here at the top, right? Chlorine. So chlorine, bromine, iodine, those kinds of things will go up here. The worst leaving group is down here at the bottom. And you'll notice that the arrows only kind of go one direction. All the arrows are pointing down or kind of go around the side, but still are generally going down. So I like to call this diagram the waterfall. And the reason we call it the waterfall is because you can really only go one direction in a waterfall, right? Once you get on a waterfall, you're going down the waterfall. You're not going to go up the waterfall. And this is a point where someone else says, well, what about salmon? Salmon go up a waterfall. Well, look, organic chemists are not salmon. So it's very simple. And it's still, my metaphor still holds together. And shut up. Okay, so imagine that we are not salmon, right? Waterfall means that we can only go, reactions only work if we move down the waterfall, right? So let's talk about that. What does that mean? What that means is, let's say that I want to take an acid chloride and I want to convert it into an ester. Right? What I need to do is I need this leaving group, this chlorine, to leave, and I need this OR group to be added in there. So we need a nucleophile that is going to add an oxygen and an R group, right? And so if we think about that for a moment, we would probably say, well, an alcohol is a good way to do that. Let's add an alcohol. And that would work. If we take an acid chloride and we react it with an alcohol, sometimes you have to heat that up, but most of the time, right, this reaction will go pretty well. Acid chloride plus alcohol, you get yourself an ester. What if you want to take an acid chloride and make an amide? Well, you'd need to deliver a nitrogen with an R group attached to it. You would just use, again, an amine. So you could use something like an amine here to convert an acid chloride to an amide. This works incredibly well. You almost never have to heat up these reactions where amides go to, or where acid chlorides go to amides. That works just fine. Right? Similar thing for acid anhydrides. If we want to replace this red group, the oxygen with a carbonyl on it, with oxygen with an R group on it, we just treat it with an alcohol. Or if we want to make an amide out of it, we treat it with an amine, and that works great. Now you'll never guess what you do to convert an ester to an amide. Okay. You use an amine, you add it together. That usually takes some significant heat to get it to go, but the reaction works just great, right? Whenever we're going down the waterfall, all we need to do is just look at the thing that we're replacing, right? What do I want to add to this group? And I can add it. Right? And the mechanism for all of these is going to be very, very straightforward. I want to do just one example of the mechanism just to kind of talk about why we can't go up the waterfall. And then we'll fill in the last couple of reactions here. Okay, so let's take our alcohol plus acid chloride example, right? We have an alcohol, we have an acid chloride. This alcohol attacks the carbonyl carbon, pushes the electrons onto the oxygen, and we get something that looks like this. Right? And now the question is, when the carbonyl reforms, because we're doing carbonyl substitution, which of these two groups is going to get kicked out, right? Which is the better leaving group? And so the question is, right, which of these is a better leaving group? Is it chlorine, or is it this OH group, or ROH group with a positive charge on it? Well, it might be the ROH group with a positive charge on it, but every once in a while is going to be neutralized, right? So if we neutralize that, and get to this, now which of these is a better leaving group? We have a much better leaving group in chlorine. And so when this carbonyl reforms, one of these two groups is going to get kicked out. Now, if we lose the OR group, we just remake our acid chloride and we can restart the reaction, and that's fine. But if we lose the chlorine, right? Like that. Now we've made something new. Now we've made an ester. I lost my R prime. Now we've made our ester. And this is not going to go backwards, right, up through this reaction again, because if chlorine were to attack this carbonyl, so imagine that Cl minus comes in and attacks this carbonyl. Let's do that one. Ooh. Chlorine attacks the carbonyl. Now, chlorine is not a very good nucleophile, so already we're kind of on shaky ground. That's unlikely to happen, but that's fine. If chlorine attacks that the carbonyl, we get this intermediate, right? This tetrahedral intermediate that once again is going to reform the carbonyl, and now the question is which group gets kicked out? And I think it's pretty clear that chlorine is a better leaving group, and so the thing that's going to get kicked out is the chlorine, and we're just going to end up back over here, right? So once we make the ester, this reaction doesn't really go anywhere because the ester is always going to, what do I want to say? The ester is just going to kind of keep being the ester. There's nothing that can replace that OR group. The chlorine can't do it, and there's nothing else in the reaction to do that. And so we can't go back up the waterfall. If we take an ester and we treat it with chlorine, Cl minus, we can't go up to a better leaving group here, right? This reaction relies on losing the best leaving group. And so whatever the best leaving group is, that's the group that's going to leave. If it's a chlorine, the chlorine will leave every time. If it's an anhydride, the anhydride will leave, right? And so on and so forth. What this means is that amides are generally the most stable. If you take an amide and react it with some alcohol, you're not going to get an ester. You're going to get an amide with an alcohol because the alcohol will keep getting kicked back out because that's going to be a better leaving group than the nitrogen. All right, so we can also convert acid chlorides to anhydrides. We just add in a carboxylic acid, right? And so then this oxygen, well, either oxygen, acts as your nucleophile, adds in there, and the chlorine gets kicked out, and you make the anhydride. So these are all the reactions on the waterfall. We go from acid chloride to anhydride by adding a carboxylic acid. We add anhydride to ester by adding an alcohol. And we add ester, or we can make an ester into an amide by adding a primary amine. Now notice that you can jump. You don't have to go through each step to get there. If you want to make an amide out of an acid chloride, you can go all the way around and just directly react it with an amine and get there. So you don't have to do step by step by step by step to get to an amide. You can just take an acid chloride, react it with an amine. Okay? Hopefully that makes sense. So far, so good, right? You have a good leaving group. The good leaving group is the leaving group that leaves, since that's what leaving groups do. If you don't have a good leaving group, you're kind of stuck. We can't go back up the waterfall. And so you might think, well, man, we're going to be stuck making, everything's going to eventually just be an amide, and then we're going to be stuck there. And so in the next video, we're going to talk about how do we get around that? Like, how do we get around the waterfall? If everything is only going down, how do we not just end up stuck at the bottom of this waterfall? And the answer is that we can convert everything into carboxylic acid. And the carboxylic acid is like the portage that goes where you carry the canoe on your head and you go up the waterfall. I'm really torturing this metaphor for everything it's worth. Trust me, this all makes perfect sense in my head. All right, come on back for the carboxylic acid part of this waterfall diagram in the next video.